In this video, we'll be talking about our first type of regression. It's usually considered the most basic kind of regression, but it's also the most fundamental towards every other kind of regression we'll be talking about from here on out. So it's called ordinary least squares regression, and the kind of idea behind it is in the name. So let's look at this graph here. We've graphed the price of milk versus the quantity of milk. So we're using price of milk as the explanatory variable, trying to explain the quantity of milk people buy. So we see this general downward trend where if the price of milk gets really high, people are buying less milk and so on. Now this is just very basic. It doesn't really capture an accurate relationship. We're just trying to give two variables, a response variable and an explanatory one. So now the idea behind ordinary least squares is this. We have all these black data points you see. Now we're trying to fit some linear curve through it. So it's important to note that ordinary least squares is linear. We have to do a linear relationship. So we're trying to fit some linear green line through it. Now you're saying, why did I pick this line? You're saying, oh, I picked it because it fits most of the data points. Well, we want a quantitative way to figure out why this line is best and why not choose, say, why didn't we choose this line instead? So you're saying I didn't choose the orange line because it's not going through as many of the points. But again, we want a quantitative way to show it. And how we're doing that is going to use squares. So we've already drawn a few squares here. So we see that under this green line, if we had chosen this green line, then we have a data point here and we have a data point here. Now what's the error? How far did we get it off? The actual quantity of milk bought for this price is this much. But we're predicting, under the green line, we're predicting it to be right here. So we've made an error. We made a miscalculation of this much. Now if we square our miscalculation, which we can do by just drawing a length the same, which is the same length as this error, and then taking the area of the square, that's the square of our error, we're going to add that into our running total of the sum of the square errors, right? So we're doing that for every single point. Now we get down to this point, we do the same thing. We see that the error is higher, maybe it's double as much. So we see that we're miscalculating by this much. Therefore our error, let's say, is double. Therefore our square error, the area, is going to be 4 times, right? So there's a big penalty here if we're making mistakes because it's going squared as the length of the errors. So we do this for every single point. We would draw a square, we would figure out what's the area of that square, and we add up all the areas of these squares. And naturally what we want is for the area of these squares, the total area of these squares, to be minimized, because if it's small, that means that we're getting pretty close to this, the actual data. This green line is getting pretty close to this data on average. Now the bad thing would be if some of the square errors are really big. So let's see why this orange line is bad. Let's just say for this point right here. If we had done this process, if we took the sum of the square, then under the green line, it would be roughly like this. So it's a pretty bad square, but it would be this much area. But under the orange line, we're going to have to go all the way down here, more than double. Therefore, the area is going to be more than quadrupled. So it's going to have this really big square, which is really bad for our approximation function. That's the idea behind it. We're trying to find the line of best fit. Therefore, we're trying to find the coefficients, the slope intercept, such that some of these square errors are minimized. And that makes natural sense. So let's go down and do the math behind it. Now what we really have is a system of equations, right? Because we have endpoints, and black points here. And each one has a P sub I, comma Q sub I. It has a price sub I, comma quantity sub I, right? So we're trying to generate some prediction function for each point. So for the first point, Q1, we have Q1 is equal to beta naught plus beta 1 P1 plus epsilon sub I. And this is our error term, okay? These are our errors. What does this mean? This means that the actual Q sub I, so let's say if this is our first point right here, the actual Q sub I, the actual quantity, is going to be given by the prediction function. So that means it's going to be that value right there. It's going to prediction function plus the error of that point. And the error of that point is exactly the distance that we did right here, right? So that is a true statement by this graph. Now we keep going, we do that for all endpoints. When we get to the nth point, let's just say the nth point is this one, just for simplicity. Then we again do, it's going to be equal to beta naught plus beta 1 p sub n, which is the linear function. It's the prediction function's value at that p sub n. So if this is p sub n, then the prediction function is right here, plus the error sub n. So again, the error sub n is exactly that distance right here. In this case, error sub n is bigger. So we have the system of equations, and we're going to represent it in vector form to kind of make it really compact. So we have this q1, q2, q3, all the way to q sub n vector. We're going to represent that as q vector, and we're going to write this whole thing right here in a matrix form. So I'll walk you through it just to make sure we get it, because I remember when I first learned it, it was a little bit confusing. So first off, this epsilon vector is easy to understand. It's just storing all these epsilons, just as this q vector is storing all these q's. So what's left to do? We need to do the beta naught plus beta 1 p1 all the way to beta naught plus beta 1 p sub n. Notice the betas are not changing. They're still beta naught beta 1 because the line is the same for all points. That's the idea. So we have this beta vector, beta naught, beta 1. It's a simple 2 by 1 vector. And this, what's the length of this, what's the size of this matrix? So it's n by 2. So let's just make sure the matrix multiplication checks out first. So we have an n by 2 multiplication multiplied by a 2 by 1 vector. So this matches because these two indices are equal. Therefore, our result will be an n by 1 vector. Okay, so that n by 1 vector in epsilon is also an n by 1 vector. Q is also an n by 1 vector. So at least the dimensions are matching up. But just to make sure you're convinced, let's just expand this out just a little bit. So we have it's ones, and then other column is the P1 to Pn multiplied by beta naught, beta 1. Now let's do some matrix multiplication just to make sure we're getting the same thing as we did in the system of equations. So how do you do matrix multiplication? You do the row and then you do the columns. So the first one would be beta naught plus beta 1, P1. And then we keep doing that. What's the last column? It's going to be beta naught plus beta 1, P sub n. And that's exactly what we have here. And that's getting added to the epsilon vector. So this checks out. This is the correct matrix vector form for our system of equations here. So now we're going to just call this matrix right here A. We're going to call this beta vector beta. So we can just write this in a nice clean form like this. And then this is equivalent to saying epsilon is equal to Q vector minus A beta vector, because we're just going to take epsilon by itself. And why are we taking the epsilon by itself? What we're going to do now is take the norm of the epsilon vector, which means we're going to take the square root of epsilon 1 squared plus blah, 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 epsilon n squared. You can, in 2 dimensions, this is like a distance, but we're doing in n dimensions here. And now this, as we just saw, since epsilon vector is equal to Q vector minus A beta vector, the norm of this is equal to the norm of this, right? So naturally, what do we want to do? We would like to minimize the sum of the square errors, right? So we want to minimize this quantity squared, because if we minimize this squared, then we're minimizing this squared, which is this squared. But we're minimizing this squared, we're minimizing epsilon 1 squared plus epsilon 2 squared plus blah, 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 plus epsilon n squared. And that's exactly what we said we wanted, right? We want to minimize the sum of all of these squares. So far, so good. We're doing what the graphic picture matches up with the equations so far. So what we want to do is find the beta naught and beta 1 such that we're minimizing this epsilon vector squared, which is the same thing as minimizing this squared, subject to the beta naught and beta 1. Now this, how are we going to solve this? Whenever we're minimizing something, it's important to use calculus. Now to be able to apply our calculus, we're going to write this in a slightly different form. Here we've written in a nice clean vector form, but we're going to write it now in just the natural form we'd see it in. So we're minimizing the sum of the square errors. So for example, this is the actual point, this is the prediction function. So this is our, right here, this is equivalent to epsilon sub I. So we're minimizing the sum of the epsilon sub I squared, which is what we see up here, right? So this is exactly what we're trying to do. We're going to give this function a name. So we're going to call it E for error function, and the only inputs are beta naught and beta 1, which we're still trying to find, right? So now to minimize this, we're going to take the partial derivative in terms of beta naught and then in beta 1, and then try to figure out how to try to solve that system of equations. So we're taking partial derivative of the error function with respect to beta naught. We're going to get this. It's pretty simple to take it. You just take the square down, because remember, if you're doing the sum of a bunch of these things, you can just take the derivative inside and take the sum of the derivatives. So we have all these right here. That needs to be equal to 0 because we're trying to minimize it. And we take the partial derivative of E with respect to beta 1. We're again doing the same thing. It's pretty much the same, except we get this P1 term because this was multiplied by P sub I. Sorry, P sub I term because this is multiplied by P sub I. This has to be equal to 0. These are very important. So I've written 1, 2 because we're going to keep track of the 1s match up with the 1s, the 2s match up with the 2s as we try to simplify this guy. So now let's just track the 1s right now. So we started with this. Now what do we get? So this 2 is pretty irrelevant, this negative 2, so we can just get rid of it since there's a 0 here. So and then we're going to try to break up this sum by all these parts, right? So we have here is a sum of qi, that's the first thing, minus beta naught n. And why am I doing beta naught n? Well, this is the sum over n points, and beta naught is just a number. So it's just coming outside the sum, and we just have the sum of a bunch of 1s, which is just n. And then here we have minus beta 1, the sum of pi, right? And that needs to be equal to 0. Now let's try to do some clever manipulations here. So we're going to go to the next one. We'll come back to this 2 when we look at the 2s. What is the sum of qi? Or more interesting question is, what is 1 over n times the sum of qi? Well, this is just the formula for the mean of the qi, right? Because you're summing all of them up, dividing by the number of 1s there are. So if we just multiply this mean by n, we're getting sum of qi, which is exactly what we had right here. So we have n times q bar, which is the mean of q. That's equivalent to what we have here. This beta naught n is still beta naught n. And then we have, again, sum of pi is equal to n times the mean of p, right? Because that's the same idea as the q thing we just did up here. Now that has to be equal to 0. Notice we have an n here, n here, n here. We can get rid of them so that we get a nice clean equation in 1 here is beta naught is equal to q bar minus beta 1 p bar, okay? And we just got that by just rearranging this equation right here. So now before we go further, let's track what happened in equation 2 so we can plug them into each other. So we started with this. The next thing we did was, again, we got rid of this negative 2. It's pretty irrelevant. And then we broke this up by parts. So we're multiplying each term by p sub i. So we have sum of q sub I, p sub I, minus beta naught sum of pi, minus beta 1 sum of pi squared. Okay? We're going back down here. What we're going to do is this, we're going to keep how it is. This, we are going to, again, call the sum of pi is just n times the mean of p, which is what we're doing down here. And this we just kept how it is. So there's not much change between these two steps right here. Now that we have this final equation for 2 and this final equation for 1, we have this in terms of beta naught. We have beta naught in terms of beta 1. We're going to go ahead and plug this beta naught into this beta naught to try to solve for beta 1, right? So we're going to plug this into 2, and it's not that hard. It's just a little bit of rearranging of terms. So we see all that going on here. We'll just skip to the good part where we're finding the answer. So we have that beta 1. I'll explain why it says OLS in a second, but it's equal to the sum of q sub I, p sub I, minus n q bar p bar, again these are means, divided by the sum of p sub I squared minus n p, the mean of p squared. Okay, it seems a little bit complicated, but it's a pretty compact formula, which is good for us. How you find beta naught OLS is simply take the beta 1 you found, put it in here, and just solve here. So I should have written OLS here. Now why is that OLS there? Why did I suddenly write the OLS? Well, this is going to come into play when we talk about the other kind of regressions we're doing, because beta naught and beta 1 are subject to the kind of procedure we're using. In this case, we wanted to find them such that we're minimizing the sum of the squares. What if we had a different strategy? It's an equally valid strategy. What if instead of trying to minimize the sum of the squares, we're trying to minimize the absolute value of the error? So instead of squaring them, we're just taking the absolute value of epsilon sub I, epsilon sub n, and so on. Then we'll get different beta naught and beta 1, and we'd have to call them something different. So since we're doing this for ordinary least squares, I'm writing OLS here just to remind us always that this is for an ordinary least squares regression, and that's the formula. So this formula doesn't hold always. It's just depending on which procedure we've decided to use. But anyway, here are our formulas. And the next thing we'll talk about is a slight nuance of ordinary least squares that's not necessarily true for other kind of regression methods. So to understand this, you'll need to know what SST, SSE, and SSR is. And we explain these. This is sum of squares total, sum of squares explained, sum of squares residual. We explain these in the R squared video, which you can see here if you haven't already watched. But the R squared video is about the metric called R squared, which measures how good does your chosen regression prediction function match up with the actual points you're trying to predict. It's not exactly a measure of accuracy, it's more a measure of explained variation. So please watch that video before you check this out, and this will make a lot more sense. So as we noted in that video, SST is equal to sum over all the points I, q sub I, minus the mean of the q's squared. So remember, it's the total variation from the mean of the data points without even considering the prediction function yet. Now we're just going to do a few algebraic manipulations here. So this inside part I'm going to rewrite as qi predicted minus q bar plus qi minus qi predicted. So if you notice, we have a qi minus qi here, and here what we have left is q sub I minus q bar. So nothing has changed so far. Now I'm gonna square this. So the first thing we get squared is q sub I predicted minus q bar squared. The next thing we get squared is this guy squared, and I guess we have the cross term. So it's 2 times q sub I predicted minus q bar, qi minus q sub I predicted, right? So this is in blue and this is in green. This is SSE as we defined it in the R squared video. This is SSR as we defined it in the R squared video. Now we noted in that video that it's not necessarily true that SST equals SSE plus SSR. In this case, in ordinary least squares, it is true. And since I'm saying it's true, that can only mean one thing. That can only happen if this cross term here is equal to 0, because it needs to go away for this to be true. So let's see, is it actually equal to 0? So this cross term, so we're going to split it up. We're going to break it up by this. So we're going to do q sub I predicted times this quantity right here minus q bar times this quantity right here. So again, we're carrying the 2 around. It's not really important. So the first sum we get is this. The next sum we get is this. So we're going to kind of we're going to expand this a little bit. So the first sum we get is this. It's 2 times the sum. And this qi predicted, we have a formula for it now, right? It's beta naught OLS plus beta 1 OLS p sub I. And we have this bit right here. Minus, so it's minus this thing right here. And this thing right here we can write as 2 q bar, because we're just, the q bar is out here. And again, we have a formula for this q sub I predicted, which is beta naught OLS minus beta 1 OLS p sub I. Now, why are those things equal to 0? So we can appeal to certain things to say why those things are equal to 0, right? So why is this thing equal to 0 right here? Well, if we go back to, let's keep an eye on both of them. So we're trying to figure out why this guy is equal to 0, right? And I put a 1 right here because we're appealing to the first condition, the first derivative condition here. This derivative condition tells us that we made the OLS such that the sum of data point y values, qi values, minus the prediction function is equal to 0. And that's exactly what we have here. So by definition, this is equal to 0. So we see that this goes to 0. Now that means all we're left with is just this part right here. Why is this equal to 0? We're going to split it up by beta naught and beta 1 OLS. So we have 2 times sum of beta naught OLS times this guy plus sum of beta 1 OLS times this guy. Now this is equal to 0 y. Again, it's by the definition of 1 because this is the same thing as qi minus the prediction function, the same thing we have up here. That's why this is 0. And beta naught OLS is just a constant, so it doesn't matter that it's being multiplied. Now why is this guy equal to 0? We're going to appeal to the second condition here. The second condition says that qi minus the prediction function times pi is equal to 0, the sum. So what do we have here? We have here qi minus the prediction function times pi. This is just a constant, therefore this is equal to 0 by the definition of OLS. So that means we've proved that we have SS total is equal to SS explained plus SS residual. And that was not true before. Now you're saying, why is this such a big deal? Now this comes back full circle to the R squared measure. So remember, we defined R squared as 1 minus SSR over SST. So kind of without the 1 minus, it's the percentage of variation, the total variation that is unexplained. So 1 minus is kind of like the percentage that is explained. But now we can take this one further, and we can write this as, if we write this 1 as SST over SST, then on the top we'll have SST minus SSR, which by this definition is SSE. So we see that in this case, in ordinary least squares, R squared is exactly the percentage of variation, the total variation in the y values, in this case the q values, that we can explain through the model. So that's kind of a big deal in interpreting R squared in this particular circumstance. So that's an ordinary least squares regression. In future videos we'll talk about ridge regressions, lasso regressions, logistic regressions, and maybe a few others.